Hi everyone, welcome to the third and final part of Chapter 1. Today we're going to work more on calculations, problem solving, and dealing with the metric system, significant figures, all that kind of good stuff. A lot of the foundational information that you are going to need for Chem 1 we're going to cover today. So, first off, we're going to talk a little bit about density. So density determines essentially whether something sinks or floats in water. Water has a density of 1 gram per milliliter, or 1 gram per centimeter cubed. And so anything that is less dense than water, so like a cork and ice, will float. So you'll see a cork is 0.26 grams per milliliter, and then the ice is 0.92 grams per milliliter. Because those things are less dense than water, they float when they're put into water. Conversely, since aluminum and lead have a higher density than water, they will sink because they have a greater density. So what I do want you to know off of this slide, I want you to know, well, A, whether something will sink or float, but also B, know that the density of water is 1 gram per milliliter. That's going to help you a lot in conversions and calculations, especially in lab as we move forward throughout the course. So here is our density equation. So density is equal to mass over volume, or D is equal to M over V. Sometimes you'll see the units of grams per centimeters cubed, and sometimes you'll see the units grams per milliliter. Grams per centimeters cubed is typically used for solids, and gram per milliliter is typically used for liquids. They mean the same thing. They're calculated essentially the same way, so they're kind of interchangeable, but that's why we use one over the other. So here's an example problem. A solid has a volume of 4.6 centimeters cubed. If the density of the solid is 7.5 grams per centimeters cubed, what is the mass in grams of that piece of solid? So we have our density equation. Density equals mass over volume, and we are trying to solve for mass. So we need to get M by itself, so we'll multiply V by both sides. Our V's cancel out. We're left with mass by itself. So mass is equal to density times volume. So we've got that. We can plug it in. 7.5 times 4.6. If you punch in your calculator, you're going to get 34.5. But if you round for significant figures, then your answer would be 35 grams. Two things. Always make sure to round for significant figures, and we're going to cover significant figures in just a minute here. But round for significant figures and make sure to always put your unit. Those two things I will be checking for, especially in your labs, and it is worth points. So if you round to the wrong number of significant figures, or you put the wrong unit or don't put a unit, you will lose points. So be very, very careful with those two things. Next topic is prefix multipliers. So we use the SI system and the metric system, and they use prefix multipliers with their standard units. And things that are prefix multipliers are like kilo or milli or centi, right? There's something that goes in the front of the unit that tells you how that unit has been modified. The multipliers change the value of the unit by powers of 10, which is why the metric system is awesome, because you're not, constantly trying to remember how many ounces are in a pound, but these always just go up or down by 10. So just like an exponent might do in scientific notation. So it works very well with scientific notation. So for an example, a kilometer has the prefix meaning kilo, right? It's kilometer, and kilo means 1,000. So 1 kilometer, right? 1 kilometer literally means 1,000 meters. Okay, so these things that go in the front, those are the prefix multipliers. And here they are. I will expect you to know these. I'm going to preface that by saying we don't use giga and mega all that much. You do need to know them in case they show up on a test or a quiz, but we don't use them all that frequently. The ones that we're going to use a lot are kilo, centi, milli. We'll use a little bit of nano. So those are the frequent flyers. Those are the ones you definitely need to know. The other ones, like I said, will show up on a quiz or a test, or they could. I would go ahead and say if you're looking for things to cut out, pico and femto, we don't really use in this class. The other ones, the ones you see the arrow by on the side, know those. So like we were talking about a kilometer, right? One kilometer literally means 1,000 meters, right? 10 to the third is 1,000, 1 with 3 zeros. So here's an example. using these prefix multipliers. It says a hospital has 125 deciliter bags of blood plasma. What is the volume of the plasma expressed in milliliters? So we are starting, oh, sorry for the sound effects, but you'll just have to sit through them. So we're looking for how many milliliters, right? So we have 125 deciliters, that's what we're starting with. And I will always do all of my work in what I like to call train tracks, but it's really, called dimensional analysis. So the way that we set up this dimensional analysis, whatever we're starting with always goes in the top left. And we're going to go ahead and make this like train track of sorts. Okay, this will usually be empty. Sometimes there'll be stuff there, but it's kind of rare. So whatever we're starting with is going in this top left, and we're always going to cancel our units down and to the right. And so I might not know the conversion from deciliters to milliliters. You might, but if you don't, you can always just go back to liters. So what I would do is I know that the prefix deci, right, D-E-C-I, means 1/10. So I know that there are 10 deciliters in 1 liter. So I'll put 10 deciliters on the bottom and 1 liter on the top. And the way that we do that, right, we can see that our units cancel. So our deciliters will cancel down and to the right. And then we're left with liters. So now I can turn my liters into milliliters. So the conversion we know there, right, we knew 10 deciliters was equal to 1 liter. And we know there are 1,000 milliliters in 1 liter. So we can continue our train tracks here by now converting our liters into milliliters. So again, our units have to cancel down and to the right. So we'll put 1 liter down on the bottom and that 1,000 milliliters up there on the top. We double check, units cancel down and to the right, and now we're left with milliliters in our last spot here, which is what we were trying to find. Okay, so when we're doing these conversions, and hopefully you've seen these before, anytime we have two things that are equal, like this, we have 10 deciliters is equal to 1 liter. Anytime we have things that are equal, they can get stacked in these train tracks. So anytime you're going to stack things in the train tracks, that means that they're equal. 10 deciliters equals 1 liter, 1 liter equals 1,000 milliliters. And to figure out which thing goes on the top or the bottom, right, our deciliters here needed to cancel deciliters down here. So we're putting our deciliter half on the bottom of this train track, and we're putting our liter half on the top so that we can continue going. And then in the next one, we had liters on the top that needed to cancel liters on the bottom. So this 1 liter portion went on the bottom of that train track, and the 1,000 milliliter portion went on the top of that train track. And I have more, if you're not familiar with how to do these, I have more examples of this train track business as we move forward. And then the way that we calculate it is we are going to multiply all of the numbers on the top and divide by all of the numbers on the bottom. So this is going to end up being 125, oops, here, let's let that click through. 125, times 1 divided by 10 times 1,000 divided by 1. So we don't need the divided by, or the ones in there. So it's 125 divided by 10 times 1,000. So we're going to multiply by anything on the top, divide by anything on the bottom, and then we'll get our answer there. Sorry, that's hopefully that was clear. Like I said, I will do more examples as we move forward. And I want to point out when we get into significant figures that these conversions, this 10 deciliters equals 1 liter, and the 1,000 milliliters equals 1 liter, those are exact. So all of the stuff on the previous page that we were looking at, all of those prefix multipliers, those are exact. So they will not kind of factor into our significant figures. So our significant figures will be dictated by this number in the front here, this 125 deciliters, because everything else is exact. Okay. Scientific notation. You should be familiar with scientific notation from somewhere, some previous math or science class, but in case you're not, scientific notation is a shorthand way to express very, very large or very, very small numbers. And our best example in chemistry is 6.02 times 10 to the 23rd, which is equal to 1 mole. And hopefully you've all had chemistry before, so that should be familiar to you. So our general form is that we have some number, which we'll say A, times 10 to some power. And that some power, right, is our exponent. So this is 6.02 times 10 to the 23rd. So this would be our A, right? And this would be our N up here. And all that means is that if we were to, write this out, we would move this decimal place to the right 23 times. So we go 1, 2, 3, 4, right, and so on. And then you would add zeros in all of these spaces. So 6.02 times 10 to the 23rd is a very, very, very large number. And you could see if you were constantly writing out 21 zeros that there might be a case where you might drop a zero, and that would affect your calculations. In addition, it's just really a pain in the butt to keep writing out all of those zeros over and over again. Significant figures. So significant figures are really, really important in measurements. And we'll talk more about this in lab. But whenever you make a measurement, so say you're going to measure the mass or the volume of something, there's nothing and no instrument that can measure the volume or the mass or whatever it may be to an infinite number of decimal places. At some point, there's always going to be some kind of estimate that's made. If you're familiar with reading a graduated cylinder, like on a 100 milliliter graduated cylinder, we're always going to estimate the hundredths place because you can't read the graduated cylinder any more exact than that because of the number of lines that are on that graduated cylinder. The same thing with, a mass, right? Say you're going to use an electric balance. That balance can only measure to a certain precision. It can't measure an infinite number of decimal places. So the last digit that it's showing you is actually an estimate. Same thing right here with these centimeter values. This is, done using a centimeter ruler. And again, we can't measure to an infinite number of decimal places. We can only measure to the hundredths place. And so if we look, all these measurements from different people are slightly different because we're always going to estimate that last value. It looks like, it was between 20.1 and 20.2, but we can't know exactly where it is between those. So we're estimating that digit. Maybe it's 20.15, maybe it's 20.16, right? And so because people are different, right, and you can't measure it that precisely, people come up with different guesses for that last digit. Maybe I said it was 20.14 and my lab partner said it was 20.15, right? So that last digit is always an estimate. Okay, so we take into account significant figures when we're doing calculations and when we're reporting a number because there is an inherent amount of uncertainty in those measurements. And so the significant figures represent how much uncertainty there is. So we will, show in our measurements, the total number of significant figures, and then as we carry on our calculations, we may have to round based on these, the number of significant figures in the measurements. So if we're looking at this, the certain digits are on the left. We know it's somewhere between 20.1 and 20.2. But that last digit we are having to estimate because we can't read the ruler that precisely. So that last digit is an uncertain digit. It's an estimate. It's still important. You still have to include it, but that is the one that may be different for different people, and that will play into how we move through our calculations moving forward. So here's some rules for significant figures in general. Okay. All digits 1 to 9 are significant. So if you see a number 1, 2, 3, 4, 5, 6, 7, 8, 9, those are significant. But the zeros may or may not be significant. So we have to follow rules to dictate whether, or to determine whether or not they are significant. So here's our zero rules. If the zeros follow a decimal point, they are significant. So this would be what we call a trailing zero. Okay, these are trailing zeros, and if they follow a decimal point, then they are significant. Our trailing zeros are only sometimes. Okay, so if they follow a decimal point there at the end, they are significant. If we have zeros between non-zero digits, they are significant. So we call these captive zeros. So say like in the number 201, that zero is between two digits, right? Two non-zero digits. So it's being captured by the 2 and the 1. So that 0 in the middle, that will always be significant. For numbers less than 1, so this would be very small decimal numbers, the leading zeros are never significant. So if we had something like 0.0034, I don't know, then those zeros in the front, these ones here, all of these, those are leading zeros. Okay, they are never significant. They're like placeholder zeros. And then zeros are not significant at the end of a number without the decimal point. So this is trailing again, okay? So there are two different types of trailing zeros. If we have trailing zeros and there's a decimal point, then they are significant. If there are trailing zeros without a decimal point, then they are not significant, okay? So captive zeros are always. Leading zeros are never, and these trailing zeros, these guys, these are sometimes. So we'll go through some examples. So how many significant figures are in each of the following? So in this first one, we have captive zeros, and we have a trailing zero. So if you'll recall from the last slide, captive zeros are always significant. So these guys, these are, yes, those are significant. Trailing zeros are the sometimes, and trailing zeros are significant if there's a decimal point. Well, here we are, there's a decimal point, so therefore it is significant. So this number has 5 sig figs. All of those digits are significant. The 1, the 2 zeros, the 7, and the other 0. This number has a trailing zero. And again, trailing zeros are sometimes significant. So that 0 at the end, right, is significant if there's a decimal point, which there is. So that means this number has 4 significant figures. Here's another one. So this one has captive zeros, so those are always significant. And this one, at the end, that is a trailing zero. And remember, trailing zeros are significant only if there's a decimal point, which there's not. So that 0 is not significant. So this number has 5 sig figs. This 0 at the end, not a significant figure. This number has leading zeros, so zeros in the front. So if you'll recall, leading zeros are never significant. So none of these zeros are significant. Therefore, this number only has 2 sig figs. This number has trailing zeros, and trailing zeros again are the sometimes, and these trailing zeros are only significant if there's a decimal point, which there's not. So those zeros, none of those zeros are significant, just the first 2 numbers. Okay, so those rules on the previous slide are going to be really, really helpful. Any numbers 1 through 9 are significant. Captive zeros, always. Leading zeros, never. Trailing zeros, sometimes, right? And trailing zeros are significant if there's a decimal point. So before, I talked a little bit about exact numbers, but there are 2 types of numbers, just in general. Inexact numbers, which are approximations or measurements. So anytime you make a measurement, anytime, that is an inexact number. At some point, you made an estimate to get that measurement, whether it was you or the electronic balance or whatever the case may be, right? Anytime you make a measurement of any kind, that is an inexact number because no instrument can measure that precisely to an infinite number of decimal places. And then you'll have exact numbers that are infinitely precise. And so these would be like counting items, like I have 3 cats. Yes, I know that's a lot of cats, but I do have 3. And I don't have 3.1, I don't have, 2.9. I have exactly 3 cats. I have 3.000000 cats, right? There's no, they're fat, but there's no denying I have 3 cats. So that would be an exact number. And then we also have mathematical constants, which we'll get into, like pi and things like that, right? If you use that pi functionality on your calculator, that would be an exact number. And then defined quantities are the ones I was talking about earlier, like 1 kilometer is equal to 1,000 meters. That is going to be an exact number. So all of those ones on that slide that talked about the prefix multipliers, these are going to be exact. So these exact numbers are not going to play into our calculations in determining how many significant figures our answer will have. We are only going to look at the measurements to tell us how many significant figures our answer will have. So just be careful about that. Measurements dictate significant figures, exact numbers do not. Okay, and your exact numbers will usually be things like this, where again, they're a defined quantity. Okay, so sig figs and calculations. Two different rules to remember. The first one is adding and subtracting. For adding and subtracting, the least precise number dictates the significant figures in the final answer. And the way this actually plays out is the one with the fewest decimal points, or the one with the fewest amount of numbers past the decimal. Okay, and you'll see an example of that in the next slide. So this one, the way that I remember this is numbers past the decimal places. And then in multiplication and division, you're going to round to the one with the same number, with the fewest significant figures. So you're just going to look at total number of significant figures in the two measurements and round to the one with the fewest. These will both make more sense with examples. Okay, this is the way that I remember this. This is numbers past the decimal. And this one is total sig figs. Okay, that's the way that I remember these two things. And again, that will make more sense as we move forward. Okay, so our rules for rounding, just throwing this in there in case you missed this in third grade or whenever they taught that. If the last digit is 4 or less, you're going to round down. If the last digit is 5 or more, then round up. Okay, hopefully we knew that, but just in case we didn't, there you are. Okay, here are some examples for how we would use these significant figure rules. So if we look in those first ones, those addition and subtraction, we're following the numbers past the decimal rule. And so in that, in the first problem, we have 2 numbers past the decimal point. We have 4 numbers past the decimal point, and if we were just to add them straight down, we would get this. Okay, but we have to follow our addition and subtraction rules, and we will round to the fewest number of digits past the decimal point. So we're going to round to here. Okay, so this 4 does not cause the 5 to be rounded up, so we can just cap it at 37.35 centimeters. If we look at the subtraction, right, again, we're going to follow the numbers past the decimal point rule. So we have 2 versus 4, so we're going to end up, right, just going right here. We're going to end up with 2 numbers past the decimal point. So in the 6 causes the 4 to be rounded up, so we get 8.25 centimeters. So that one is the one where I said those are the numbers past the decimal point. The easiest way to do this, honestly, is to line them up like this. I know you were taught how to do this in second grade or whatever the case may be, but line up the decimal points of all of your numbers, and then you can literally just draw a straight line from the one that has the fewest numbers past the decimal point, and then round your answer. I know it sounds a little bit silly, and a lot of us don't like to work things out like that, but it is really, really helpful and is an easy way to figure out how many significant figures my answer should be. People have much more difficulty with the addition-subtraction rule than they do with the multiplication-division rule. One, because you have to kind of write it out like this to see how many digits your answer should have, and 2, we just don't use it as frequently. We use the multiplication-division rule all the time, but we don't use the addition-subtraction rule as frequently. So for the multiplication-division rule, like I said, that one is total numbers of significant figures. So in the first number, we have 4 sig figs, and in the second number, we have 6 sig figs. So when we round our answer should be rounded to 4 significant figures. For the division one, again, we have 4 sig figs, and in this one we have 6 sig figs, so our answer will be rounded to 4 significant figures. And again, make sure our units are all playing out as they should. But there you go. So for the addition-subtraction rule, like I said, you're going to follow the numbers past the decimal point. Since this one only had 2, our answer is limited to 2 numbers past the decimal point. Again, this one had 2, so we're limited to 2 numbers past the decimal point. With multiplication division rules, we're looking at total number of significant figures in the number. So there are 4 versus 6, so our answer has 4 significant figures. And then 4 versus 6, our number has 4 significant figures. And again, follow all of those rounding rules. The 3 does not round up the 8, but the 5 rounds the 6 up. Okay, so be careful because I do look for that kind of thing. Here are some common equalities that you may run across. The ones that I have in red are ones that you need to know. And they're ones that you likely know already. Like 1 foot is 12 inches, there are 3 feet in a yard, 1 pound is 16 ounces. The other ones, the other US ones, I would give you if you need them, as well as the other metric US ones. You need to know 2.54 centimeters is an inch, but the rest of these I would give you. These ones are exact. This one is not. Okay, well here, we'll make that one an X, not exact. The other ones are exact. But these ones here, if you needed those or if you needed those, I would give you those on a quiz or a test. Everything in the metric you need to have memorized. But again, that's all going to be those prefix multipliers, right? Kilo means 1,000. And then, milli means 1,000th. But you need to know all of these and you need to be able to use them whenever you're doing conversions. Okay, so know the ones in the red boxes and then know all of them in the metric or SI. All right. Last slide, some equalities problems. So the first one is, how many feet are in 10.2 miles? And so we could go back and look, okay, what is our conversion that we know, miles and feet? So we know 1 mile is equal to 5,280 feet. Okay, so since we know that, we can actually go ahead and do this calculation. So we'll put 10.2 miles in the beginning here, and then we'll go ahead and make our train track. So since we know miles has to cancel miles, our miles portion of this needs to go on the bottom. So we'll put 1 mile on the bottom, and that 5,280 feet, that will go on the top. So miles cancels miles, we're left with feet, which is what we were trying to look, what we were looking for. And so we can go ahead and calculate this. So we can go 10.2 times 5,280 divided by 1, and we can get our answer. And so when we get our answer, we will need to round our answer to the correct number of significant figures. So since we have 3 sig figs here, 3 sig figs here, our answer must have 3 significant figures. So we're getting 53,900 feet. Okay. Let's try the next one. So this one says, how many kilometers are in 1 millimeter? So 1 millimeter will go in the beginning of our train track here. And we can think about our equalities that we know. I always go to the base unit like I did before. So I know that there are 1,000 millimeters in 1 meter. And I know that there are 1,000 meters in 1 kilometer. So those two things together will help me get to my answer. So we have millimeters up here in the top left. So millimeters has to cancel millimeters. So this part, that will go on the bottom. 1,000 millimeters and 1 meter will go on the top. Again, whenever things are equal, they get stacked in the train track. So millimeters cancels millimeters, and we're left with meters on the top. Now we can turn meters into kilometers by continuing this train track. So again, meters has to cancel meters, so this part will go on the bottom. So we have 1,000 meters, and so meters cancels meters, and 1 kilometer on the top. So we'll have, 1.0 times 1 times 1 divided by 1,000 divided by 1,000. And that will get us 1.0 times 10 to the minus 6. So when we're looking at, and I'm just going to draw an arrow there. When we are looking at significant figures here, you might be thinking, oh, you know, this 1 meter and this 1 kilometer, they only have one significant figure. And you'd be right, except for the fact that those are exact. Okay, 1,000 millimeters equals 1 meter. That is an exact quantity, defined quantity. Kind of like 1,000 meters equals 1 kilometer, that is a defined quantity. So our number of significant figures is only being determined by this number in the front, that 1.0 millimeters. So that's why we have this 1.0 times 10 to the minus 6 kilometers. You could also have written it as, you know, you could write out all the decimal points like that if you'd like, but then you need to include this 0 at the end, because there's 2 significant figures here, 2 significant figures. Next one. How many ounces are in 50 kilograms? So if we look back at the previous slide here, we can find kilograms to pounds, and then we have, you know, pounds to ounces. So we'll use those two. So we have 1 kilogram is equal to 2.20 pounds, and 1 pound is equal to 16 ounces. So it says how many ounces are in 50 kilograms? So 50 kilograms goes in the top left. And again, kilograms has to cancel kilograms. So kilograms will go on the bottom. And 2.20 pounds will go on the top. And this is not exact, just an FYI. 1 kilogram equals 2.20 pounds is not an exact quantity. And then so kilograms cancels kilograms. Now we're left with pounds, and we can convert our pounds into ounces. So if we continue on, now our 1 pound can go on the bottom, and our 16 ounces can go on the top. Pounds cancels pounds. We're left with ounces on the top, which is what we are looking for. So now we can do 50 times 2.2 times 16 divided by 1 divided by 1, and we will get our answer. So sig fig-wise, we have 4 significant figures here, 3 here, and this, like I told you guys before, this is exact. Okay, so our answer should have 3 significant figures. If you're confused right now about which ones are exact and which ones are not, and how to keep that all straight, 1, it will get easier. 2, mostly we're not going to deal with all of these metric US and US units. That's kind of just for this chapter. As we move forward, we're pretty much only dealing with the metric system. And all of these here are going to be exact. So you won't have to worry about it really past this first chapter. All right, last one. It says convert 1.19 meters squared to centimeters squared. And you're like, I don't have meters squared or centimeters squared. I have meters and centimeters, but I don't have meters squared and centimeters squared. Really, really easy. So we have 1.19 meters squared, and we know 1 meter is equal to 100 centimeters. So the way that we're going to do this is we're going to cancel our meters with our meters. Okay, so 1 meter is going to go on the bottom. Even though this says meters squared up here, we're going to put 1 meter on the bottom and 100 centimeters on the top. But if we think about this, that 1 meter on the bottom is only going to cancel out 1 of those meters on the top, and we'd still be left with 1. So what I like to do is I just put squared around this. So now I have 1 meter squared on the bottom over 100 centimeters squared on the top. Another way to do this would have been to not do the squared. You could get rid of that. And you can just make another train track and say 1 meter and 100 centimeters. So this one cancels out 1 of the meters on the top, and this one cancels out the other. So now we've canceled out both of those meters on the top. Either way, totally fine. It's going to work out the exact same way. So we'll end up with 1.19 times 100 times 100 will get us our answer. And both of these 1 meter equals 100 centimeters are exact. So we're going to take our 3 significant figures from that first number, and that will be how many significant figures there needs to be in our answer. I did want to make a note back on the second example problem because I don't think I mentioned it. When you're typing that in your calculator, that, 1.0 times 1 times 1 divided by 1,000, make sure you hit then again divided by 1,000. Both of those thousands are on the bottom of that train track in that second example problem. So if you're punching it all into your calculator in one line, make sure to put divided by 1,000, divided by 1,000. If you put divided by 1,000 times 1,000, it's going to think that this last one is on the top of your train track and your answer will come out incorrectly. So just something to be careful of. Make sure you hit divided by for everything on the bottom. And that's it. That is the end of chapter 1. So make sure, the trickiest part, I think, is this last bit on doing all of these conversions. Make sure you are getting solid at significant figures and solid at conversions and solid at those metric equalities. Okay, those are probably the 3 most important things from chapter 1 because we will use them for the rest of the semester. You will be responsible for knowing how to do these conversions pretty much in every single chapter for the whole semester. You will need to know significant figures for every single lab, for every single quiz, for every single test, and you will need to have those metric conversions memorized. So the sooner you start working on all of those things, the better. Again, I would check out that chapter 1 lecture worksheet. I mentioned before, the lecture worksheets are provided for you so that you can get really, really good at this stuff before you go and try the homework on Alex. The lecture worksheets are posted. The answer keys are also posted, so you can go through and work them out and then check your work and make sure that you are doing them well. I have found that people get really frustrated with the Alex homework because they don't do the lecture worksheets first. Do the lecture worksheets, get really, really good at doing them and checking your work, make sure you have the process right, and then move on to the Alex homework. That is my best advice to you for this course, is do every single lecture worksheet problem. I've done them so that you can have access to them, so that you can practice them, so that you can be successful in the course. And as always, if ever you have questions about any of the problems in the slides or in the lecture worksheets, on the study guide, in the Alex homework, on the labs, please send me questions. You can send them to me via Remind if you'd like, or you can send me an email, however you want to get a hold of me, but please, please ask me your questions and don't just be, frustrated by yourself. Anyway, next time we will start chapter 2, so see you next time.